All right, so this is meant to be a recap, number one, of the notes that we're taking today and tomorrow, technically, for your AB schedule split. What is this, October 26th and 27th? So for those of you who are out, not able to make it to class, or missed the day of the exam, you're making up the exam, whatever it might be, maybe you just want to recap. This is horizontally launched projectiles, and really all the information that you're going to be able to need for that particular unit. Or at least for that first half of the unit. Now, the first thing I want to mention is right here where you see the key new equations. There are absolutely none. And this is one of the things I talked about a lot in class today, or tomorrow, as I will soon, is this is a recap or reuse, I should say, of Unit 3. We're not using any new equations. We're literally just going to take the equations that we had from Unit 3. We're going to, over these first couple of days, apply them to horizontally launched projectiles. The next couple of days, we're going to apply them to vertically launched projectiles launched at angles, like you see in the picture right up here. But that's really going to be all we're doing. There's going to be a couple of steps, but I don't want you to feel overwhelmed. So before I get too far into it, I want you to notice that you have the steps required for all of your horizontally launched projectile problems and the steps for your projectiles and angles. What follows in the packet are going to be examples of how we use these, but these are the steps we're always going to use. So with that being said, because we should have already watched the Mythbusters episode over whether or not a bullet fired or a bullet dropped from the same height hit the ground simultaneously, or which one hits the ground first. Obviously the answer is they hit the ground simultaneously. Since that should be, already in our heads, that little mental image should already be there, I wanted to walk through assignment 2 and at least the first part of assignment 3 before we move into the homework. So, linear motion versus projectile motion. Linear motion was literally just our one-dimensional stuff, and we started with our drop problems. So that's what we're going to do here. And in our first example, we're going to talk about what would happen if someone dropped a ball, a rock, whatever it might be that they drop, and allow it to fall. So each second it falls, it's going to cover a slightly different distance, and we want to draw that detailed diagram of what it would look like as it's falling freely under gravity's influence each second. One thing you should recognize for a drop problem is that your initial velocity is always going to be 0, and that gravity is the thing making it fall. And so the only other thing we're going to have to worry about is how long it's falling for. Every second that it falls, it's going to increase its speed by 10 meters per second. But that doesn't tell you how far it fell, and that's what we're plotting here. So the equation we're going to use, because initial velocity is 0 and we're looking for distance, knowing time, we're going to jump right into d equals 1/2 at squared, just like we would have from our last unit exam. Now, I did leave out the VIT part at the very beginning of this, right? It should be d equals VIT plus 1/2 at squared. But if your initial velocity is 0, then there's no point in including that. So literally all we did in class together was in your first second, we plugged in 1 second for time. After 1 second of free fall, this object is going to fall down 5 centimeters. Or sorry, not 5 centimeters, 5 meters. So it falls down 5 meters, right? 1 squared is 1, multiplied by -10, divided by 2 is going to be a -5. In our second, we get 1/2 of -10. Again, 2 squared. This is going to be 40, -40, divided by 2 is going to be a -20. And so this arrow is then going to extend all the way down to -20. It's falling down 20 meters. If it falls down 20 meters, then, after 2 seconds, that's going to be its new displacement, its new distance. Notice, and this is what I was trying to get at a moment ago when I stumbled over the words, or just a second ago, the distance that it falls every second, you'll notice as we go to do this, is going to increase. Every second it falls further because every second it's moving faster. And so you'll notice that after 3 seconds, it will have dropped a total of 45 meters. And then after 4 full seconds, it's going to drop a total of 80 meters. The total distance that I set this thing to be up as, right? So that's how far it's going to go. This was our drop problem. This is what we did in the last unit. This is actually the exact same problem that was in that data table on the Unit 3 review guide. So this should not be new. What we are going to do is we are going to apply that to horizontal motion. And what we should have recognized in the Mythbusters episode, in the very last statement that Adam, I believe it was, not Jamie, Adam leaves you with, is that motion in the horizontal direction for a throw, a horizontally launched projectile, is completely and utterly independent of the motion that you get vertically. Because the only thing that causes your speed to change is gravity, and gravity only works up and down. It doesn't work left and right. So if you throw this even with any sort of velocity to the right, like we're doing here, at a time of 1 second, after 1 second has passed, it will travel some horizontal distance, some horizontal displacement, maybe 5 meters, maybe 10 meters, just depends on how quickly it's moving. But vertically, after 1 second of motion, it will have fallen -5 meters every single time. And this comes back to our vector addition stuff, right? At the tip of your first vector is when you begin the tail of your next vector. So after my horizontal displacement, moving to the right, I'm then going to have a vertical independent displacement that's going to go down 5 meters because that's how far an object falls in its first second. After it's traveled to the right for 2 seconds, it will have fallen, let me get these lined up, 20 meters. After 3 seconds, it will have fallen 45 meters. And after 4 seconds, it's still going to do the same thing. 4 seconds is right there. I'll go all the way down to the bottom. I want to make sure I get my things lined up here. I'm going to go all the way down to the bottom. It will have fallen all 80 meters. So the point behind having this little diagram, this little visual, is that whenever we're doing any of these problems, this is why your stuff, your projectiles, will always follow, let me zoom out a little bit more, that same, and I'm going to nerd this up real quick, I'm going to use the same term your math teacher would use, the same parabolic trajectory that we have always witnessed every horizontally launched projectile to follow. Right? This is why they follow that sort of trajectory right there, why they have the shape of that path that they follow. It's always that parabolic sort of shape because we're doing this vector addition. But notice the only vector that ever changes, the only acceleration occurs in the vertical direction. The horizontal direction doesn't change. Had we thrown this at half the speed, then it would have hit, 5 meters vertically right there. It would have hit 20 vertically right there. It would have hit 45 here, and it would have hit 80 all the way down to here and traveled half the distance. If we doubled the distance, the horizontal speed, then traveling double, it would have been 5 there, 20 here, 45 all the way out here, and then in the next one, I should have gone over more. Yeah, 20, 45, all the way down here, right? If we doubled its speed, it's going to continue moving a little bit faster. It's going to cover more distance every second. So you're going to be able to extend that out a little bit. And that's the main idea. So whether or not you drop in the first scenario an object from 80 meters, it'll hit the ground in 4 seconds. Or if you throw it horizontally, it will hit the ground in 4 seconds because your vertical motion, again, up and down, and your horizontal motion, left and right, are completely independent. Completely independent of one another. Motion left and right doesn't influence what gravity does. In fact, in the not next unit, but the unit after that with gravity, I can mathematically prove to you that your mass, at the very least, is irrelevant in terms of the acceleration due to gravity on the planet, right? The fact that you are present or exist here on the planet does not influence the acceleration due to gravity that the Earth experiences or exerts on other objects, and I can back that up with a calculation. It's kind of fun. But that motion, right, because your mass is irrelevant when it comes to gravity, that motion that you might be undertaking is also irrelevant. It doesn't matter what it is you're doing, moving left and right, moving up and down. In terms of moving left and right, that motion is completely independent. So what I did in class was I did for assignment 3, unit 4, assignment 3, 2 of these 5 problems with you. I want you to do 3, 4, and 5 for homework, but I'm going to walk you through how we do these steps. From the cover page, step number 1, we are always, just like we did on the last page as well, treating this as a drop problem. We're going to use the height, the vertical distance, in order to figure out exactly how long gravity is going to let this object stay in the air. And we're using 1/2 AT squared. So we've got a vertical height that it's going to fall down of 2 meters. 1/2 gravity is still -10. And then we've got time squared. We need to close those parentheses. It's going to bug me if I don't. In this particular problem right here, we've got, what is that, -2 multiplied by 2 is going to be -4. -4 over -10 is going to be 0.4. So I'm going to get 0.4 is equal to t squared. I stopped there so that I could remind you guys that you have not finished yet. You've got to take the square root of both sides. So your time is going to work out to be 0.63 seconds that this tennis ball is allowed to be in the air for. Now, in that 0.63 seconds, it is also moving left and right. Once it hits the ground, notice that this arrow stays the same every single time. Once it hits the ground, it's no longer able to move to the right. So we use our next equation. Since there's no sort of horizontal acceleration, this tennis ball doesn't have a rocket strapped to it. It doesn't have wings that allow it to flap and produce lift or thrust or any of those things. We can go back to our very, very, very easy equation of v equals d over t, because all we're doing is solving for how far it can go. It doesn't speed up or slow down left or right. It does accelerate vertically, but horizontally it does not accelerate. So using this equation, we can get a horizontal distance of, 1.5 multiplied by 0.63. Again, your units are meters per second multiplied by a second, so the seconds cancel out. And you're going to get 0.95 meters. And there it is. In this particular scenario, I do want to point out that it is tricky if we're not specific and probably more than anything intentional in how we label these distances, because I want you to notice in number 1A there's a distance, and number 1B there is another distance, and they are not the same distances. I did not plug in letter B anywhere at all. So one of the things I do that I really like to do is I am going to label my equations with a subscript of the letter Y, in order to differentiate what happens in my y-axis, up and down, from what happens in my x-axis, left and right. That way I don't get dy and dx mixed up, ever. If that doesn't help, then one of the things you can also do that I highly encourage people do is 2 things. Number 1, draw a picture. So for number 2, I've got a person standing on top of a cliff. Lots of cliffs. Never seen this many cliffs around Chicago, but lots of cliffs. Standing on the top of a cliff, throwing a rock down. We know that it's going to follow that parabolic trajectory that literally everything we've ever observed has followed. There's a couple of pieces of information that are provided here. So I'm going to use both the picture and a data table. Yes, I'm using a data table to separate my x and y components so that I can keep them straight and use them in the appropriate equations. So first thing I'm given, a horizontal velocity of 12 meters per second. I'm going to label that Vx is equal to 12. All right, it's meters per second, so right off the bat I know it should be a velocity. I also tell you it's a velocity, so that should be easy. But it's horizontal, and so it's going to be in the x direction. They ask how far away, so I'm looking for a distance, will the rock land? The distance that the rock lands is also horizontal from the base of the cliff, so they're looking for dx. I don't know what that's going to be. Probably going to be measured in meters because my speed was meters per second, so I'm going to keep that unit of distance. If the cliff is 25 meters high, I'm going to label the height of the cliff as 25 meters. I know that value, but what I also know is that that rock is going to fall down those 25 meters, so this is my displacement in the y direction. It's a negative because it starts up there with him at 0 and falls down the 25, but the reason I separate these two is so that you recognize, and you will always recognize, that 25 and 12 should never be in the same equation together. That is the crucial detail. That is the crucial point. That is why we do it this way. Other things that we do know is that acceleration in the y direction is -10, right? It's gravity. There is no acceleration in the x direction, so I could write that down as a 0. You don't have to write it every single time, but it is something that we know. You could do it. Other things that we know is that this was launched horizontally, so my initial velocity in the y direction is 0. I'm not throwing this up into the air, and I'm not throwing it down into the ground. I'm throwing it horizontally, and I'm not giving it any up or down motion at all at the beginning of the problem. Later on, I'll describe that as momentum, but I'm not giving it anything. And the only thing that both of these directions, both of these axes, have in common is time. Notice the x-axis has 2 unknowns, distance and time, and the y-axis only has 1 unknown. This is why we always start step number 1 with our vertical stuff. It's a drop problem. How long, this is essentially what you're asking yourself, how long will gravity allow that object to be airborne? And once gravity will no longer allow it to be airborne, find out how long it's in the air, time, that's how long it's allowed to also move left and right. And that's how we break up these two problems. That's all these need to be. So we've got a -25 is equal to 1/2 of -10 multiplied by t squared. So 25 multiplied by 2 is 50. We've got 5. The square root of 5 is 2.24 seconds. So my time in the air, 2.24 seconds. I'm not done yet. That's just how long it's allowed to move left and right. Now, at what rate is it moving left and right? We're able to use dx is equal to vx multiplied by t because this rock does not have wings and it does not have a rocket strapped to it. It is not accelerating left and right, which is why I'm able to go back to the really good old school v equals d over t. Of course, I rearranged it because I don't like fractions. It's a personal choice, but it's entirely up to you. So in this particular case, your horizontal displacement is going to be equal to 12 meters per second multiplied by your 2.24 seconds. Your units of seconds will cancel each other out, and you're going to get a horizontal displacement of 27 meters from the base of the cliff. All right, if it traveled faster in those 2.5 seconds, 2.25 seconds, if it traveled faster, it would go further. If it traveled slower, it would not go as far. But notice that the height of the cliff is what determined, the height that it fell is what determined how long it was in the air for. And it's always going to be these same 2 steps for all of these problems. Find out how long it's in the air for with our drop problem, our drop equation, and only your vertical distance and acceleration. Then once you know how long it's falling for, you know how long it's allowed to move left and right. And you can use v equals d over t. That's it. So for homework, I wanted you guys to try number 3, number 4, number 5. You don't have to do all of these individual steps. So label those variables, draw your picture, identify what you have available to yourself, and it should make a lot more sense. But we will definitely, obviously, go over these once the due date has passed. So if you've got questions, comments, or concerns, never, ever hesitate to reach out and ask. But that is what you would have missed the second half of the day on Monday or Tuesday, the 26th or the 27th.